So work, energy, and power is something we started in grade 11, and we started doing that when we're looking at Newton's laws. So work, energy, and power is a continuation of Newton's laws, and I'm going to systematically deal with this topic and connect it. Make sure you are in the flow once I start connecting. Now let's look at the word work. The word work. So I'm going to just flow like that. Work, energy, and power. Work. What do I know about work? First, let's start with the symbol. Symbol is W. Units. Joules. Symbol W, unit, joules. Quantity. Work is a scalar quantity. That's a very important point that we would need. Work is a scalar quantity. That's going to come in very handy somewhere along the line. Now, when do we say work is done? So please make sure you connect, and if you listen carefully, you won't need to read again. You just need to do practice and calculations. When do we say work is done? Work is done when a force applied on an object causes a displacement. Because I mentioned force now, we're going back to grade 11. Work is done when a force applied causes a displacement. Displacement means distance, right? From a reference point. That means if I am pushing a wall and the wall is not moving, I'm not doing work because my displacement will be 0. So what is the formula? W is F delta X cos theta, where my W is work measured in joules, F is force measured in newtons, grade 11, delta X is my horizontal displacement measured in meters, cos is a trig ratio, and theta, very important, angle between F and delta X. That's very important. Theta is the angle between F and delta X. Theta is the angle between F and delta X. I always like to stress all the variables and stress the units so that you are well prepared for applications. It therefore means that 1 joule can be written as 1 Newton meter. N force, M displacement. So we are saying F times displacement, which is Newton times meters. So 1 joule, and definitely you know that angle theta, I mean, it's just a number. Cos 30, if I say cos 30, it's just a number. Cos 60, it's just a number. And the number has no unit. So 1 joule is that. That is very, very important. You'll find this in multiple choice. When we are done, you're going to see how many formulas we are going to come across. I'll keep creating the formulas for you. Now we are going to look at all of these variables one after the other. One after the other. So please follow through. This is the introduction. We are going to look at these variables one after the other. Work being the last one. Work, or let's start with work. Let's look at the variable of work. So there are three types of work done. So I'm looking at W, variable W. There are three types of work done. How are you? Three types of work done. Number one, positive work. Number one, positive work. What does it mean when we say positive work? Energy is transferred to the system. Energy is transferred to the system. Energy is transferred. So I give you all these notes for multiple choice purpose. Energy is transferred to the system. If that happens, the kinetic energy of the system increases. Of the system increases. If that happens, speed will increase. Speed at which the object is moving, speed increases. Speed at which the object is moving will increase. Are you aware that I've already created 3 points? So I can create my multiple choice already. I just put one rubbish now, and which one is not an impact of what? Positive work. For positive work, energy is transferred to the system. If I push you now, what happens? Your speed will increase. So I am transferring energy to you. That's positive work. Kinetic energy work, increase. Speed will increase. I'm going to give you one more. Theta, and this angle theta is between 0 degrees and 90 degrees. When that happens, I'm going to have positive. Because if you check this, we're in the first quadrant. Let's go back to tree. And cos of any of that angle is what? Positive. In the first quadrant, we're dealing with angles that are acute, and all the trig ratios are positive. Number two, negative work. And I'm sure you can write the whole story now. Looking at my point, what happens? Energy is what? Removed from the system. Energy is removed from the system. So what happens? The system actually loses kinetic energy. Kinetic energy of the system decreases. And if the kinetic energy decreases, what are we saying? The speed decreases. And when will this happen? When theta is between 90 degrees and what? 180. Where does that take you? Inclusive of 180. Where does that take you? That takes you to the second quadrant. And what's happening? Cos is what? That's where the negative work comes from. And number three, I want to squeeze it here. Oof. Number three, let me try to squeeze everything here. That's number one. Number two. And number three. We're still going to look at this theta to understand all of this. Number three, Zero work. Zero work. When I say zero work, what's happening? No changes in energy. No changes in energy and speed. And when will this happen? Theta must be equal to what? 90 degrees. Because if I check my calculator now and press cos 90, 0. So if I put that cos here, cos 90, 0 multiplied by all of this, 0. So we have three types of work: positive work, negative work, and zero work. Positive work will add energy to the system. Negative work will remove energy from the system. Zero work, redundant, does nothing to the system.
Isn't that for vertical forces?
Okay, we're going to get there, but since you asked, theta is the angle between the force and the displacement. So any force that has an angle of 90 degrees to the displacement, and there are only two: normal force and FG perpendicular. These are the two that will not do any work on an object. Okay, we'll move on. We're now going to grade 11. We've looked at that. We're going to look at this and link it up to this again. This is where the work is, F. So we got to run on this. And I'm going to treat you as if you don't know anything from grade 11. Forces. Our second variable is F. There are 5 forces that we're going to look at. And these 5 forces, I'm going to categorize them quickly. So I'm going to compress because of time. I'm going to categorize these forces into 2. Contact force and non-contact force. And just from the word contact and non-contact, contact means something that is touching. So let's go back to our grade 11. Give me all the forces and then we're going to be categorizing them. Okay, force applied. It's contact. I cannot push something I am not in contact with, except if it's spiritual now. And all of a sudden, if the table in your class starts moving, that's the end of school for me. Okay, so applied force is a push or a pull. And that is what? A contact force. So applied force. Number 1, applied force, which is a push or pull. It must be in contact. Number 2, friction. Beautiful. Somebody's thinking air friction. It must be in contact with the air. Friction. Let's define friction. Now, please, guys, definition goes beyond words. I'm still going to look at all this forces, but there's something I want to quickly achieve here. All right, so beautiful. A force exerted by a surface, and what type of surface, by the way? A rough surface, on an object parallel to the surface and what? Opposes the direction of motion. And it's a contact force. I cannot talk about contact if the object is not in contact with, or friction, if the object is not in contact with the surface. Number 3, tension. Beautiful. What do we know? Force in a string. Let me do something nice. Let me do something nice. I want us to remember something. I'm going to write this in a different letter. What is here? A. What is here? F. And what is here? T. Look at those letters. Can you create a word? A word that makes sense. Could you just give me a word?
Third.
After. How? 3 letters. AFT. Somebody mentioned something now. Fat.
Fat.
Fat. F-A-T. Friction. Applied. Tension. Those forces are contact force. It's going to help us later. You would see why fat is important. Fat. When I say contact forces, they are fat forces. Give me examples of non-contact. We said there are 5 forces, remember? Any other force? Gravitational force. Now, do you think gravitational force is a contact force? No. If you jump up, are you in contact with the earth? No. But it pulls you down, right? Lovely. So that would go under my what? So gravitational what? Force. How would you define that? Force of earth, pulling force of earth on all objects. Pulling force of the earth on all what? Objects. Remember, and which way does it act? Wrong. It doesn't act down. Sorry to bust your bubbles. Perpendicular to the earth. Wow, Shamil. It doesn't act down. I'll tell you why. Why you're wrong by saying down. Do you know all those forces are pointing down? And not all of them is gravity. So can we fix it? Act where? Vertically downwards. That's very important. Gravity acts vertically what? Downwards. Now, what about normal force? Okay, I want you to check something. I am not going to add normal force to this list because it's doing no work. Although it's a contact force, but it's doing what? No work. Okay, let's just add it as part of contact force. Number 4, contact force. But I am going to put a star on it. Why am I writing contact? What are we saying? Normal force. I'm going to keep stressing that it does no work. So we have our 5 forces. Interesting. There's something I want to point out here. Facts, ne? Friction, applied, and tension. Normal, no work, or with contact. And then we have gravitational. Yes. I'm going to give you another force that is not in this topic, but is non-contact. We're going to put a star on it for knowledge's sake. I've seen them ask this question. What is it now? Electrostatic force.
Yeah. Oh, I know what you're saying. Electrostatic force.
because it's either attraction or repulsion. The charges don't need to touch each other. Remember, they pull each other. So I once saw a question that says, list 2. Now, they didn't use the word non-contact. I'm going to go to the other words now. Okay? Now, so, these forces that we've listed as contact or non-contact can be divided, can be renamed as this. Contact forces are called non-conservative forces. While non-contact are called conservative forces. Check something there. Do you notice that the word non has changed? Contact are non-conservative. Non-contact are conservative. The question is, what is a non-conservative force and what is a conservative force? It comes as a definition. It's 2 marks. The contact forces are non-conservative. So let's quickly define what are non-conservative forces. And you will see why I'm grouping them now. Force whose work done, we are looking at work, right? Remember? Depends on the path taken. Force whose work done depends on the path. If it depends on the path, there must be contact. I don't know if that makes sense. If it depends on a path, path is your way. So there must be what? Contact. And what are these forces? Fat. So my non-conservative forces are fat. And what does fat mean? Friction, applied tension. Friction, applied tension. So, can we then define conservative forces? What are my conservative forces? Force. Who's what? I'm telling you why I'm writing this work done in capital. Learners forget that. A learner would write force whose depends on the path taken. And that's wrong. Force whose work done does not depend on the path what? Taken. And I'll quickly show you another way that I usually remember this. When I say none, there's no none in the definition. But there's no none here, then there's a not. It must contain a none. I don't know if that makes sense. When I say non-conservative, depends on the path. When I say conservative, does not depend on the path. There's always one none. And the only force we are going to look at under this is the force of what? Gravity. Okay, we're moving good. Ooh.
So what do you call the force in a spring? It's a conservative force. Or what do you call
Spring. Tension. It's a contact force. If it's a contact force, it's a non-conservative force. No, it's not. Why? A force in a spring, tension is an applied force. If I'm pulling you through a rope, I'm not really pulling you. I'm pulling the rope. The rope is pulling you. So the rope, the force in the rope is an applied force. And because it's an applied force, it is a contact force. And contact forces are non-conservative forces. So keep the acronym FACT. It's going to really help us as we look at questions. Okay. You know, I can decide not to even look at forces in grade 11 and just move on. Your Newton's laws. Do I need to go there? Free body diagram. No, man. Can we just fire on? Okay. And I'll check your free body diagrams as we go on for calculation. Can I do that? Okay. Just to quickly wrap things up. Okay, so we said WF and what? Yes, talk to me. I've got a hand there. All right. We will deal with that. What's going to happen is when we want to look at activities, we're going to be looking at question 2 and question 5. Newton and that. Make sense? So that instead of us revising and wasting time here. So when it comes to activities, we do Newton's work energy. Newton's work. So let's fire on. Beautiful. Thank you so much. Thank you. Now, so guys, I am done with W. I am done with F. What's next? Theta. The angle. Beautiful. Usually what makes me take long is I start now looking at what is a normal force, what is, grade 11 work. Theta. But we want to quickly complete this one. Theta. I'm going to meet you here. I'm going to say something. I'm going to say some things very, very emphatic, and it's always, just take note of those. What is theta? That's the first thing I want us to learn. The angle between the force and what? The displacement. The angle between the force and the displacement. If I look at my forces, applied force. Okay, we're going to look at two things here. Let's look at horizontal and inclined. Let's start with the horizontal one. Horizontal surface. Horizontal what? Surface. If I have a horizontal surface and I have an object, this is where we are going to use our free body diagrams now, right? If I have a force this way, and I say the object is moving, you've got to look at where the object is going. Let's make this a rough surface. Where will friction be acting? To the left. Okay, so if I were to draw a free body diagram, what forces do I have? I have my normal force. I have my gravitational force applied in this direction and friction in that direction, right? Please watch this. So we have force applied, we have our normal, we have our force of gravity, and we have kinetic what? Friction. Why kinetic? Object is in motion. Where is your displacement? How is the object moving? Object is moving to the right. I want you to take note of this. If I look, I'm going to draw these forces now and split them. Because once I create this foundational understanding, we're going to fly. It's going to be easy. Look at my applied force for F. How is the force acting? To the right. Right? How is my displacement? What is the angle between them?
0.
Beautiful. Theta is 0 degrees. So when I see that they are in the same direction, theta becomes what? 0. What type of work is this?
No.
Positive work. Well, actually, let me do something. Let's go back there and let's put inclusive of 0 there. Because 0 is 1. Okay? Cos 0 is 1. So just put it there under positive work. But not inclusive of 90, remember? So what work is this? Positive work. Beautiful. Positive work. Let's look at normal force. I'm using white for my forces, and I'm using green. Normal force. What can you tell me? The angle between them, 90 degrees. Theta is what? What type of work? Zero work. Why zero work? Because cos 90 is 0. Are we together? We're splitting all of this. We'll bring everything together now and we'll be done. What's next? Friction. No. Object is moving that way. And how is the force acting? What's the angle between them? 180. Why? Angle on a straight line. What is this? And I want to quickly tell you something here. For friction, theta is always 180 degrees. It will never be 0. It would never be less than 180. It is all why? It opposes the direction of motion. So it is always what? 180. And that's going to be your guide when you draw a free body diagram. Theta is always what? 180. What about FG in this case? FG. Whether I measure clockwise or anti-clockwise makes no difference. If you check your calculator, what is cos 90? What's cos 270? 0. It makes no difference whether I'm going clockwise or anti-clockwise. When we get to a slope, that's why I'm looking at a horizontal surface now. When I get to a slope, then I have to be specific by saying FG perpendicular and FG parallel. So here, theta equals to what? 90 degrees, and we talk about what? 0 work. So the answer lies in the free body diagram and the definition, knowing the definition of the forces. Let me know if we are okay so far. Let's see. I've been talking alone. Are we okay so far? Is it making sense? Please pay attention to your free body diagram. You know, that's one thing that people just draw nonsensically. And that's the answer, whether you're doing Newton's laws, that is your answer. Theta is the angle between F and delta X. Can I ask you a question? Can force applied and friction act in the same direction?
Yes. Yes. And it's if your mind is pushing the car upwards, but the car is still going down.
Okay, don't let's go on a slope. Let's stay horizontally.
Yeah. Where is the object?
Doesn't matter, you just create it. It's just a general question. Can friction and applied act in the same direction?
So if the definition says that you always don't Yes.
Sorry guys online, just hold on, I'm just listening to something that you said.
The definition says we're moving in the opposite direction, doesn't it just be constant that friction is always against?
Yes.
I want you to go back to the note of friction that you wrote. Opposite direction of what? Of the motion. No one said of the applied force. Right? Okay, those of you at home, somebody is talking. I heard two voices now. Oh, I'm seeing answers. Yes, 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 yes. Look at your car when you are approaching a robot. What do? You apply the brakes. Where is the brakes acting? It's acting opposite because it's stopping you. Any force that is stopping you is acting against you. Makes sense, right? So if I am stopping a car and I apply the brakes, don't be deceived by me pressing forward. That's just a system. But really, the brakes are acting what? In the opposite what? While the car is moving forward. Makes sense? So in that case, my F is going to be 180. I always use friction to judge my system. Any force in the direction of friction, I write 180. Any force opposite friction, 0. That's why we always resolve to have vertical and horizontal what? Components. So that the two angles I'm using are 0 and 180. Let's look at an inclined surface quickly. Inclined surface. An inclined surface. And my good learners, right from grade 11, you have been taught wrongly. Right from grade 11, there's something I'm going to ask you to delete from your brain. Please delete. What is this angle? What do we use? Theta. Please delete it. You will be confused. So please delete it. I would never teach you in grade 11 and write theta there. I write alpha. Because we are going to get to a place where we write two thetas in one formula and they mean different things. It doesn't make sense. It's like saying solve for y if y equals to 2x plus x. And I'm telling you that this x is different from the, spell school. And then you do this. And I say, no, it's wrong. Why? This O is supposed to come here and this O is it doesn't make sense. It doesn't make sense. So please, I know you are used to this as theta, but let it sink in that that's alpha to create the difference in the what? Angles. Remember, I want to keep my definition of theta. What is theta? The angle between the force and the displacement. While alpha is the angle of inclination. I've always raised that when I do teacher training and teacher meetings, that guys, can we change those things? Especially in grade 11. Because it becomes difficult now when as I'm talking now, some of you are still seeing theta. So please work with me here. Let's have an object. And I want this object to actually be moving down. I want this object to be moving down. Remember, I'm using green for my displacement, right? I want this object to move down. But we are pulling up. Is that possible?
Yes.
Yeah. Probably the object is heavier than my force. Okay, like Shamil pulling something down, you know. Force applied. Rough surface. Can we draw a free body diagram? What will it be? I wonder, what forces do I have? Normal force. How is your normal force? Let us just still get this wrong. Perpendicular. Yes, I know. But how? Which one is correct? Huh?
The second one.
The first one.
Okay. None of them. AB. Which one is correct?
A.
It's A. Let us just draw that normal force, and I'm wondering. Look, the whole idea is this. This is what I do. If I have a surface like that, this would be my normal force, right? Okay. I want to do something for you. Before I do that, 90 degrees, right? Because the definition says it must be perpendicular. Now, if I rotate my surface, makes sense? If my surface is the other way around, why? I must maintain that angle of what? 90 degrees. So it's very, very important. I see a lot of people just draw normal force and then draw it straight. I'm like, no, guys, how many free body diagrams have you been drawing since grade 11? Okay, so my normal force is that way. Are we okay? My normal force is that way. Thank you guys for those beautiful answers that you gave me. Where's my force of gravity?
Down.
No way, it's not down. Vertically what? Downwards. Shamil, be here. FG. No, what is this? Normal force. Okay, where's my force applied? Just look at the diagram. All right, upwards, there. Where's my friction?
No, the same direction.
Because the object is moving down.
Object is moving down. Friction says it opposes the direction of motion, not applied force. I don't know where learners get applied force. I just put it inside the definition. No, motion. So I look at my motion to determine my friction. If object is coming down the plane, friction must move in where? Up the plane. Don't worry, friction has nothing to do with applied force. Is that okay? All right. So my friction is that way. Is there any other force? No. Now remember, we don't work with this diagram. What do I do? Components. I'll tell you how I draw my components to make it easy for you if you can follow it. If I'm drawing my components, I start by my normal. Once I draw my normal, I draw my what? FG what? Perpendicular. The word perpendicular should always guide you. It is perpendicular to the... Let's draw a surface. Let's draw a surface just to make things clear. Let's put my surface as blue surface. So you would see the angle 90 and 90. Hence the word perpendicular. Where's my applied force? Oh, hold on. Since I have drawn FG perpendicular, I need to draw FG what? And again, this drives me nuts when Elena draws FG going up. Guys, if we say FG parallel, two things are involved. FG is going down. Parallel means parallel to the surface. So parallel. Now there are two lines that we can draw here that are parallel to the surface. That's why be mindful of the things you say. Parallel. That's parallel to the surface, right? Also parallel to the surface. But one is parallel up and the other one parallel going. But we are talking about FG, which is always acting where? Good. So now how do we draw my FG parallel? That way. So if you are not sure, draw the surface. Make sense? Are we okay? Good. I've seen learners draw this. And I'm asking, where is the surface? It's because we don't pay attention to definitions. Hello, Naledi.
Hi, sir.
Hi, Nana.
I always get confused by the direction of FG parallel, whether it should be like going up or down. Like the way you drew it, but like whether it should be on the other side or the one that you drew it. So how do you determine the side it should be on?
Okay, keep your mic on, lady. That's what I just explained here. FG is going where? Down. And what?
Parallel.
To the? That's why I'm saying if you are confused, draw the surface. Can you see my surface?
Yes, sir.
Now, if I ask you to draw a line parallel to the surface, look, if I draw this, is it parallel to the surface? No. So that's out. If I draw this, is it parallel to the surface? Yes.
Yes, it is.
But FG cannot act upwards. It has to act where? Down. Are we sorted?
Yes, sir.
So if you're welcome. If you are confused, just draw a line to represent what? The surface, and link the words to it. Down and parallel. That's the only down and parallel line.
Or if you're confused, think about this. Throw yourself down the staircase. If you go up the staircase, FG parallel is
So, yes. So in an exam, I'm going to ask you to go to the toilet. But I'll come back damaged. But it makes sense. FG never goes where? Up. Anything that goes up must come down. Are we okay? Thank you, now, lady, because I know when I move around and I see that particular diagram being drawn wrongly. So the key is, and you know if you mess it up now, you'll mess it up in question 2. It's 2 and 5. And they won't say, oh, this child messed it up in question 2. Let's give the learner in question. It's a different person who's marking. A different person is marking question 2. A different person is marking question 5. So the person marking question 2 has nothing to do with your question 5. No, MCQ everybody marks. When we mark, so if I'm starting your paper and I'm marking question 7, if I'm the first person who receives your paper, I mark question 1 and question 7. So somebody is marking question 1 and question 2. Somebody is marking question 1 and question 5. By the time your paper comes to me and question 1 is marked already, I just go to the question I'm marking and I carry on. So I don't know whether you missed free body diagram in question 2, then I say, no, this child, let me have mercy. I don't care about your question 2. I just get my question 5 and I mark. All right. So like I said, 2 and 5 been dealt with now together. Good. What about applied force? You look at the diagram. Applied force is where? Are we good? Then you look at the motion. How is the object going? Down, right? So that's my delta x. So we pay attention to details. How is my friction acting? Opposite the direction of motion. Always. So my friction. Guys, I want us to fix all our angles now. Please let me know if everyone is okay here. If we get this right, I promise you calculation becomes the easiest.
So are you saying that the gravitational force parallel is greater than the applied force?
No. FG is going down because gravity acts downward. That's just it. And it's parallel to the surface. It has nothing to do with the normal. It has nothing to do with any other force.
I understand that. What I'm asking is that it's going down if the applied force is smaller.
It depends on the size of the object. We cannot say. Those things depend on the size of the object, the angle at which the object is raised. So we cannot determine, we're not looking at which one is bigger, which one is smaller at the moment. We're just looking at the direction because those things can change. I'll have certain cases where FG parallel is bigger than normal. I'll have certain cases where normal is bigger than FG. It depends on the size of the weight of the object and the angle of the object. But right now we are looking at the definition of the forces and putting it accordingly. Now, what did I say about friction? What's the angle? Theta. Theta is always what? Beautiful. I don't need to think anymore. It means in this case, the theta for F is 180, the theta for friction. So friction is my guide. Friction is always what? 180. Oh, which angle would this be?
0.
Does that make sense? Because it's a straight line. If that is 180, that is 0. By the way, can you see that both of them are acting in the same what? Direction. And these other two, what would it be? 90 degrees. 0 work. Make sense? Now, quickly, grade 11 again. What is my FG parallel? MG sine alpha. I know you were pausing. You're already saying theta in your heart. MG sine what? Alpha. And what is this one? MG cos. Please don't mix these things. FG parallel is MG sine. I'm going to show you a way to run away from using that. But you must know it. There are certain questions where you don't have a choice. There are questions where you have a choice. If I have a choice, I don't use it. And I'll be showing you how to run away from it. Because so that you don't mess things up. Now, guys, if I tell you that what is the work done by applied force? Do you remember my formula for work? It is F delta X cos theta. I'm only going to be changing the force. So what is the work done by applied force? Which force am I using? F applied delta X. I am now being specific, right? I'm going somewhere with this. If I say what is the work done by frictional force, what will it be? Frictional force delta X cos theta. Are you with me? If I say what is the work done by FG parallel, what will it be? Let's start with this. FG parallel delta X. But what is FG parallel? MG sine alpha. Do you see why I used alpha? Because if I were to keep it as theta, this is where people get confused. Now they don't know which angle is this, because we now have two angles in the question. We have theta, alpha, and we have what? Theta. But if I do it like this now, I'm sure it helps. Because I know that alpha is my angle of what? Inclination. Guys, if you just understand what I've done in 56 minutes, we are almost clear with work, energy, and power. Is it making sense? Let me take questions wherever you are lost before I move on. Ribotilio, what am I repeating? Naledi, your hand is up.
So can you please repeat the statement about 182?
Tell me what you understand.
Sir?
Tell me what you understand, Naledi.
So, like, I don't understand, like, the angles, like, let's say couple for a moment.
Okay, all right. What is theta again? That's where we need to start from. What is the angle theta? What is theta? Angle between what? The force and what? The displacement. Keep your mic on. I need us to go forth and back.
Yes, sir.
What is theta again?
The angle between the force and the displacement.
All right. Do you understand this page?
Yes, sir.
You understand this page?
Yes, sir.
Then we're good. Do you understand this page? So I have my free body diagram, right?
Oh, okay.
So all I'm using, look, the first explanation I gave you is to look at the direction of the force and the direction of the displacement. If they are in the same direction, you see, what's the angle? 0. If the displacement object is moving this way, but my force is going that way, what's the angle? 180.
Because it always must be.
Angles on a straight line. And with this one, check normal force and my displacement. What is the angle there?
90.
Look at FG perpendicular and the displacement. What is the angle? 90.
90 exactly.
And conclusively, I said, once you draw your free body diagram correct, friction is always what? 180. The one that is on the other side of friction, 0. Does that make sense now?
Yes, sir.
As my summary. Once you draw a free body diagram, friction is 180 degrees. It will never be 0. It would never be anything. It's always what? 180. And the force that is opposite on the other side becomes what? 0. I want us to learn how to use just 0 and 180. And I'll show you just now. Are we okay then, lady?
Yes, sir.
All right. You're welcome. Felix? Rubotlile, you said I should repeat. Have I repeated? I'm not sure what you said I should repeat, but I need to know. Felix, let me know. Hand is raised. Felix, hand is raised.
You don't need to repeat anything, sir.
You're good.
Yes, sir.
Okay, awesome. Yep. The light is fading. Don't worry. It won't fall on me. Really? Okay, hold on guys, 1 second. Okay, we're good. Lovely. And the rest is simply what? Substitution. Now, let's move on quickly because I want us to complete this and we're just left with what? Activities. But so far so good, I think we're okay. We just need to put all the pieces together. Now, there is something that we call work energy theorem. Work energy theorem. Once we start looking at questions now, you will see that we have actually done everything. Work energy what? Theorem. Here I have two words. Work and energy. I want you to think like this. Once I say work and energy, on one side of the equation, there's work. What's the symbol? W. On one side of the question, there's what? Energy. Okay, beautiful. Now, but before we go on, let's look at how many types of energies do we have? So many. But in terms of this, energies, let's quickly just go through. Number one, kinetic energy. And let's define. What is it? Energy of an object in motion. Do we remember the formula? EK equals to what? Half mv squared. What is m? Mass. What is v? You're wrong. Speed. Energy is a scalar quantity. So if I say velocity, velocity is what? Vector quantity. All right? So half mv squared. We're good.
In momentum, can we substitute direction?
Because momentum is a vector quantity. That's why we talk about east and west.
When we're doing that, where we prove that the energy before is equal to the energy after the variation.
Yeah, we don't substitute direction. Why? Because it's a squared. It doesn't even matter. If it's negative, moving the opposite and you put -2 squared, the negative disappears. It's a principle of maths. It's a principle of maths. Okay, number 2. Gravitational what? Potential energy. What is that? Let's define quickly. Energy of an object due to its position above the ground or above the Earth's surface. Do you remember the formula? This is grade 10. EP equals to what? mgh. Mass, acceleration due to gravity, and the height. Number 3. Mechanical energy. Mechanical what? Energy. And what is this? The sum of kinetic and potential energy. Please, this one is not on your formula page, so it's something you need to remember. Emech equals to what? EP plus EK. Emech equals to EP plus EK. Now that I've looked at all of that, I'm going to look at my work energy theorem. It's free 2 marks. When I say an examiner asks that, I just tell myself this examiner is kind. The work energy theorem is right there on your formula page. You just change it into words, that's all. And it's almost, I think, 99% in every paper. Work energy theorem. And remember what I said about the work energy theorem? One side of the equation is what? Work. So it's going to be work net delta EK. Without me saying anything, can you put that into words? Put it into words. What do you have on the left hand side? Total work, net work is equals to the change in 2 marks. 2 marks. You're done. I can open a random paper now. We'll find it there. The net work done, let's make it fancy, on an object is equal to its change in kinetic what? Energy. Please give me a reason why Elena should get that wrong. Do they get it wrong? Yes. And I feel like smacking them. Yeah. Somebody's writing law of conservation of mass or something. It's a proton, work is a proton donor. Something out completely. So guys, that's 2 free marks there. You forget, just go to your formula. It's work and energy. There's a formula that connects your work and your energy. And when I say work net, what does it mean? Sum of all the work. So we are saying work done by applied, work done by free, whatever force that is present, whatever. But remember, I don't need to say work done by normal. Zero. I don't need to say work done by FG perpendicular. It's zero. So I'm talking about work done by friction, work done by applied, work done by tension, work done by FG parallel. Okay, are we okay? I want to compress all of this content. Are we okay, everybody? Please, that's free 2 marks. Now I want us to build on this. There's something I want us to deal with. Early this year, we did what? The law of conservation of linear momentum. Can somebody help me with that? All right. The total linear momentum in an isolated system is conserved. In physics, every time we talk about an isolated conservation, we always refer to isolated system. So, when I do this, I always tell learners to define the law of conservation of whatever. It's the same thing. The total whatever in an isolated system is conserved. Those words don't change. I just need to change my whatever. If I say momentum, my whatever becomes momentum. If I say mechanical energy, my whatever becomes mechanical energy. And you did this in grade 10, where we say mechanical energy at the top is equal to mechanical. I don't know, people just come to grade 12 and behave as if they've never heard that before. You are lying. I can even remind you, we used to talk about the tower of something in France, where we drop a phone. Lies.
The law of conservation doesn't change.
So we say that, I'm going to write it down. The total, whatever they ask you to define, remains conserved, but it must be conserved in an isolated system. Okay, so let's go back to our work net. I'm going to do something here. I want us to expand this formula quickly and use it. So, can I say that work net, therefore, let me go to a fresh page. Before I go to that law, I want us to expand this formula. How do we use it? Work net equals to change. Every time in physics, if we say change, what do we say? Final minus what? Initial. Always. And what is the formula for kinetic energy? Half mv squared. But check, I am saying what? Final here. Right? Minus half what? Initial. What's common? Mass in half. So what do we say? Half m v vf minus. I'm going to come to that. Not half m. This is wrong. That one of them is a difference of 2 squared. The other one is a binomial. So please take note. Don't factorize the squared. That's wrong. Not that. It is squared and squared there. So this is my work net. Are we okay, everybody? Work net is, so that's the formula we're going to use to calculate. Work net is 1/2m. Please don't take this 2 outside. Once you take it outside, it means completely different thing mathematically. Let's do some physics. When I say physics now, I want us to mix masala. I want us to conjure things together. You ready for me? You sure? Equations of motion. There's one equations of motion that has this. Vf squared equals to what? Plus 2a. If I move this one here, what would I get? VF squared minus equals to what? Now, here I'm trying to show you something. Can I take this back there? We're just doing mathematics now and enjoying ourselves, right? So, therefore, work net can then be written as what? 1 over 2m into 2a delta x. I want to show you how we got the formula for work. The half and the 2 can actually cancel each other, right? So what do I have? W net is equal to what? MA. Oh, ma. What is that? Beautiful. What was the formula for work? Our first formula we wrote. What was work? F delta x cos theta. That's my F delta x, and my angle is now what? 0. Can you see where we've gone 360 now, and we've gone back to our original. So if an examiner asks me to calculate W net, we can also use this, especially if we are not given, excuse me, check something. Excuse me quickly. Ta-da-da-da-da. You know where I'm going? You know where I'm going, right? You know where I'm going? No, not Northwest. Northwest was kind. At all. No ways. I just hope I remember. Guys, 1 second. 1 second. I'm in that zone. I'm in that zone. Oh, I'm in that zone now. Come on, come on, come on. One second, guys. We're gonna love this. No, it's not this paper. It's not this paper. It's not this paper. Oh, it might be it. It might be it. It looks like it. It looks like it. Tell me it is the one. No, it's not. It's not. It's not. It's not. It's not. Oh, I think I know. Okay, I'll find it. I'll find it. I'll find it. Before we leave, definitely. I know it's not this one. Just give me 2 minutes of you just enjoying the versatility of the papers, but I know it's not this one. No, it's not this one. But I see the paper now. But what happened in the paper was we were not given velocities. But I'll find it before probably we leave. We're not given, but we're given acceleration. So it's a matter, we're given acceleration and displacement. And the examiner was asking for work net. So Leonard came here and they got stuck. Why? This was not given and that was not given. What was given? Acceleration and displacement. Can you see that if I just use this equation, I'm done? That since I know my acceleration and my displacement, if I put it here, whatever I have here becomes this. And I can take this and put it there, and I get my work net. I'll find it. It's from Houghton. Very lovely piece. I can see the question in my head. And I know the problem. It's just a year. And I know it has a 9. I remember opening this in 2017. I remember I was in class. I stood there and I opened it. Was it the 14? Or 16? I'll check my laptop. Okay. All right. But do you understand the beauty of, so with physics, write what you have and you can conjure equations together. Are we okay? All right. So we have W net is F net delta X. Now let's do something interesting. Look, I'm going to finish my content now. And then when we come, you know, it's just activities. Okay. What is an isolated system? Let's talk about that quickly. Conservation of mechanical energy. Conservation of mechanical energy. Can I just write EMEC? First, what is isolated system according to physics? Anybody? A system? You thought I would finish. No, I'll stop at the system.
We know outside forces.
I think
No, it's not
the system where external forces equals 0.
Yeah. No outside, no external, but the examiner wants us to use a particular language. Thank you. A system where the net external force is what? 0. So I'll write it like this. Do you remember this? What is that called? Sigma F external. What are my external forces? Fat. My external forces are, all right, anybody who's not in this class and sees your note and sees external forces are fat, they won't understand. They think we're talking about structure. And we're not talking about structure. What are we talking about? Friction, applied, and tension. Those are my fat forces. Yes, talk to me. Vukudo?
Hi, sir.
Hi.
When I think of why we use isolated system in physics and closed system in chemistry.
All right, that is what, that is as per the exam guideline. In physics, we use the word isolated. In chemistry, we use the word closed. Closed because it does not exchange material with the external. So it's a language per topic or per subject question, although the ideology means the same. Physics, we use the word isolated. Chemistry, we use the word what? Closed. Okay. Because isolated talks about, isolated talk about forces. Then in chemistry we say closed because we talk about interaction, exchange of matter. All right, external forces are what? Fat. Now, let's quickly state the law of conservation of mechanical energy. Law of conservation of mechanical energy. I'm sure you can state that now. What would you say? Okay, I like to say in an isolated what? System, the total mechanical what? Energy. And don't forget what your mechanical energy is. Is what? Conserved. Don't forget what mechanical energy is. What is mechanical energy? The sum of kinetic and potential energy. The sum of kinetic and potential energy. Okay, we're getting somewhere now. We almost clear with the whole thing. In an isolated system, the total. And what does that mean? Guys, once I say mechanical and I use the word potential, height is involved. Height is what? Involved. That is, look, I could either have it as something like that, where we're saying A, let's call this B, and let's call this what? C. Why am I saying height? Because I'm saying potential energy, which is mg what? H. So we're saying the EMEC at point A is the same as the EMEC, do you remember now, at point B, that you did this in grade 10? Oh yeah, EMEC at point C. Hi Shamil. You were not there. EMEC at point A is equal to, because we're saying nothing is removing energy from the system. Energy can neither be created nor destroyed, but transformed from one form to another. Okay. Now, what is EMEC, by the way? EK plus what? EP, which is what? Half mv squared plus what? Okay, wait. This is the maximum height. Let's bring in vertical projectile motion. What do you know at the maximum height? Minus b over 2a. This guy. Velocity is what? 0. So if I put that there, what's happening? We are saying this value is what? 0. So what is my EMEC at point A? It is basically the same thing as potential what? Energy. But at point B, EMEC therefore now becomes what? mg height of B plus half mv velocity at B. That is not 0. I'm going to explain something to you that might help you understand this. At the bottom, what do I have? H is equal to what? 0. Yes? Whose hand is up there? Tando? Hi. I'm listening to you, Tando. Tando? You ain't talking again. Yes?
That the exercise, which is FAT. I wanted to know the meaning of the FAT.
Okay, friction, applied, and tension. Friction, all right. Applied and tension. Quickly, I want us to see what I did on the right hand side. What do you notice at point A? My mechanical energy is potential. At point B, both. At point C, kinetic. Please, I want you to picture something. When I'm in grade 10 and I explain this very beautifully. To say, I'm working with someone. So imagine I'm working with my wife now. Together we are the bishop's family. Right? Good. We have a bank account where all the money we have is ours. Okay, check this. I'm not working. I'm the lazy bum in the house, doing no work. I just sit down. I'm Netflixing the whole day. My beautiful, hard-working wife goes to work, collects her salary, comes back home and says, "But baby, because I love you so much, this money is ours." Okay, she earns 50 grand. Wow, okay, lovely. She earns 50 grand. She comes home and say, "Baby, this money is ours." Why? We're a family. Is that okay? But really, it's hers. So if they ask, can I draw a diagram? Because I need my beautiful wife to be here. Okay, so here is me, and there is Susan. You remember Sue? Sue baby from organic chemistry. Come on, Sue. When we got married in the United States of America,
Oh, yeah.
I was single and seriously searching, went to the United States of America and met my baby called Susan, and her name is what? Sue. Okay, so this is me and Sue. Sue earns 50 grand. I earn 0. So somebody's asking me, how much do I have? I'll say 0. Sue, how much do you have? 50,000. Then they ask us, oh, the common lawyers, the bishops, how much do you have? We have 50,000 with a smile on my face. But really, I got nada. Okay, think of that as a height. When we start coming down, what happens? Do you notice the height is decreasing? And as the height decreases, the potential energy decreases, but the kinetic energy increases. Vertical projectile motion. When a free fall, an object going down, what happens to the velocity? Increases. Oh, now I am converting my wife's money to mine. After moving a distance, I now have 10,000. My wife has what? 40,000. Do you notice it's a conversion? Energy is not lost, but converted from potential to kinetic. As we keep going down, what's happening to the velocity? Increasing. My money now increases to 20,000. My wife would have what? Okay. And as when we get to the floor, where the height is now completely 0, I have scanned my wife. Complete scanning. She now has what? I keep telling her, baby, I love you. You know I'm going to take up the house. And then she can say, oh, baby, I'm transferring. Until she transfers everything to my account. But wait, at any point in time when they ask us how much we have, what do you notice? We maintained what? 50,000. But doesn't mean we have the same at each time. Mechanical energy is conserved, the total of kinetic and potential. But as one decreases, the other one will increase. I'm going to draw the graph for you of the relationship between the two of them. Is that making sense, guys? But mechanical energy is conserved in an isolated what? There is no external force. Then somebody cries for help. External. That will definitely affect the system. So if this person cries for help and we give this person 5 rand, because we're kind, right? We gave this person 5 rand. Now there's an external involved. What am I going to have at this point? 49,995. Do you notice mechanical energy is no longer conserved? Why? External. For me to get my 50,000 back, I would say mechanical energy plus, you got to think of physics like that. And what is the name of this external force? This guy is fat. Are we okay? Please, that is important. That guy is fat. But if that guy is not there, we okay. It's me and my baby. I'm busy scamming her until she's fully scammed. But once that guy comes in, we lose energy. Why? The system is no longer what? Isolated. So whenever the examiner is going to ask you to use the law of conservation of mechanical what? Energy. What do you need to say? You just need to say that E-mech at point A will be the same as E-mech at point what? B. You would even see, we're going to do questions where the object is swinging like a pendulum. Now what am I drawing? We're going to have something like that. Let me do this. An object is there, held stationary, and that object released would come here and we have that. Object is released and moves that way. And this, I did this when we're doing momentum, where the object then collides. Can you see physics now? We are doing work energy now, but we are connecting it to what? Momentum. This part here is where we use our mechanical what? Energy, because there's a height involved. So mechanical energy at point A will be equal to mechanical energy at point B. What is the height here? Height is 0. The examiner can put a height here. It doesn't matter. We use the same system. We just substitute. Half mv squared plus what? Mgh will be equal to what? Half mv squared plus what? Mgh. Where this one is initial, final, and final. Mechanical energy initial is equal to mechanical energy final. We are going to apply this shortly when we look at questions. Please, are you okay with my explanation? I don't know if it makes sense to you. The law of conservation of mechanical what? Energy. In an isolated system, that fat guy must not be present. Is that okay? In an isolated system, our money remains our money. But once that fat guy shows up, the guy disturbs our system. The system is no longer isolated. So mechanical energy is no longer what? Conserved. But if that fat guy is not there, mechanical energy at the top will be equal to mechanical energy at the bottom.
Could you use this principle, but also, let's say when you get to the bottom, you add in what they got to.
Yes, we are going to have questions like that where we have to now add the 5 rand. But when we get there, you will have understood the whole concept. Are we together? Is this making sense? Good. I want to finish up by, because I want us to look at one question. But I want to finish up by now bringing to you the boss of all formulas. All of this is now called energy principles. Yes, talk to me. There's a hand or somebody saying something there. No one. Lovely. Guys, I now want to bring to you, so all of these are called energy what? Principles. Energy principles. Okay. Energy principle formulas. And we'll do something nice just now. And then go to power. Energy principles. Basically, we're talking about formulas that require what? Energy. What is my first one? W net is equal to what? Change in kinetic what? Energy. That's my first energy principle. And what is that called? Work energy theorem. Number 2, EMEC initial is equal to what? EMEC final. And we know what EMEC is, right? I like repeating so that it stays. What's my EMEC? Plus potential energy. No. This is the only formula on the formula page. Now there's one more formula on the formula page, which is the boss. That formula is the boss, and that's my number 3 formula. WNC is equal to, there's no time to, I would have loved to prove how we arrive at this formula, but there's no need. What does W stand for? Work. What does NC stand for? Non-conservative. So this is called the work done by By the way, what are my non-conservative forces? Set forces. So, can I say that work done by non-conservative is work done by friction, applied, and what? Tension. Will that make sense? Facts. Because my non-conservative forces are what? Facts. Friction, applied, and so please don't forget that. We wrote that earlier on, right? Non-conservative forces are friction, applied, and tension, which is fat. So if I then go and talk about a fat-free, what am I talking about?
Conservative force and non-conservative.
And which would be what type of system? Isolated system. Wait, because if a system is isolated, there's no friction, there's no applied, and there's no tension. So fat-free is what? Isolated what? System. Please, is it making sense? Exactly. And we don't need fat. So we buy fat-free milk all the time. Guys, are you with me? I'm finishing now. Look, I just wanted to lay a good foundation for work, energy, and power. And once we get into calculation, we're just going to have a sweet flow. So please, before we look at calculation, go through these notes just 1 hour before the calculation, so we don't have to repeat. Fat-free. Okay. When I say fat-free, I want us to derive something very beautiful. Work done by non-conservative in an isolated system, what will it be equal to? I want to lead you to answer, and I want you to respond. In an isolated system, what are we saying? There's no friction, there's no applied, and there's no tension. But we said work done by non-conservative is work done by friction plus work done by what? Applied, right? Plus work done by what? But in an isolated system, is there friction? Okay, if friction is not there, can it do work? If applied is not there, can it do work? If tension is not there, can it do work? So in an this one I need you to underline it and highlight it. The work done by non-conservative is 0. Once I see that the system is isolated, the work done by because these guys are not there. A day you are absent at school, are you working at school? People are submitting. Are you submitting? No.
So would this be a case of calculating the mechanical, equating mechanical initial and mechanical final?
It's going to lead us there.
And once you prove that they equal, it means that it's
Conserved system.
And the follow-up question that it asks.
Don't let me predict the follow-up question. I don't know what it could be. It could be just anything.
No, I'm not saying it's always like that, but if they want to know if it's an isolated system, then you have to.
No, they'll tell you. They'll tell it, and if they don't tell you, you pick it up from the system. They'll tell you there's no friction. And the object has no applied. An object is moving just on the surface without being, remember, applied, there must be a push or a pull. I want us to look at one question. We're just going to randomly pick one. A push or a pull. In looking at one question, we're going to analyze and quickly break it down. Is that okay? And calculate. So you would see. You have a question?
F applied, right? It's a contact force.
Yes.
So it's a push or pull.
Push or pull. Mm-hmm.
It's initially push and then like you don't have like a push escape and I'm not pressing down.
Then there's no applied force. It's like vertical projectile motion. An object is thrown.
Yes.
So you've got to be in contact to throw it, but once your hands leave the object, it's now a free fall. Applied force is no longer there.
Okay.
Make sense?
You wouldn't account for it.
No, we're not counting for it now. For me to say there's an applied force, it must be in contact with the object throughout. So I am pulling throughout. Immediately I stop pulling, applied force is out. We okay? All right. Let's do something quickly with this formula. I want us to enjoy physics now. So in an isolated system, the work done by non-conservative is what? 0. Guys, this formula is the boss. Number 3. I use it every time. So let's do it on a fresh page, and I want to look at the question. I think I'll look at the content of power in our next lesson and then calculate. Look at this. Work done by non-conservative. What's the formula? Change in kinetic plus change in what? Potential. There was a question from Free State some year where they asked them to use this formula to prove that mechanical energy is conserved in an isolated system. So watch this. If the system is isolated, what do we know? Non-conservative is what? It's important. That's why I'm repeating. So what would that be? 0 equals to, what is this? EKF minus what? EKI plus MGH final minus MGH initial. Or let's use EP since I'm using that. EP final minus what? EP initial. Are we okay? Every time we say change, it is final minus initial. Let's expand these formulas. Or before we expand, let's move all the initials to one side. You see where I'm going already? So what will I have? EK initial plus EP initial EK final plus, wait, what is this? Sum of kinetic and potential. Oh, what is this? E mech initial equals to what? E mech final. And we have simply proven what? The law of conservation of mechanical what? Energy. We are done. Let's look at the question. I'll start with power in our next class. I'll start with power and finish power. Work done by non-conservative in an isolated system is 0. I want us to look at one question. Guys, are we okay? Did this make sense? Trying to just make it simple, break it down, and enjoyable. People cry about work, but it's so simple that somebody sang with it. Work. I mean, that's how simple it is. You know, work. I don't even know the lyrics. You know? And yet, my precious learners, what don't you understand? Work! Guys, somebody sang with it. You guys are laughing. So it's so easy somebody sang with it. Think of it like that. Don't cry. The idea is read, draw your free body diagram, and you're done. Read, draw your, once you read, you're able to see the forces. When you draw your free body diagram, you're able to see the angles.
But the substitution can be done like this.
No. Maybe it's because how you...
Like substituting our page.
So look at how many formulas you gave us for this.
But the formulas are on the formula page. Listen, no. This formula is there on the formula page. And it's from there I'm deriving this. No. I just use this formula and I substitute. That's all. All I do is, I don't need to derive this. I just use this formula and put a 0 there. And I continue my life. Easy. Too easy. Okay, come. Let's find a question. This question, does it have power? Oh, 10 marks. Okay. I think it will be a good hello, work energy and power question. Beautiful. Beautiful. 10 marks. Let's see. 10 Beautiful marks. Guys, it's about reading. I know you don't like reading, and that needs to stop. 10 minutes, 10 marks. Okay, so we're going to walk through together. And whatever we do here will set a precedence to how we do other questions. We start by what? Reading. I want to show you how I read. A cyclist pushes. Some of you are already done. You're already on the 20 Newton. Can you push without being in contact? So what is the word pushing telling you? There's a contact, which is what? An applied force. A cyclist pushes his bicycle of mass 6.1 kilogram up the incline with a force of what? 20 newtons. The bicycle is pushed, the examiner is emphasizing, pushed from an initial velocity of what? 5 from point A. Can I just write the 5 there so that it makes it easy for us to see? Velocity here is what? 5 meters per second to point B. The road is inclined at 10 degrees. What is that? Alpha or theta? Alpha. All right. To the horizontal and a distance of what? 32. This distance is what you know as what? Delta X. Okay. This one is always what? Height. As shown below. The road surface exerts a frictional force of what? 11 newtons on the tire. Please, before we start, free body diagram. Everybody, quickly. Draw your free body diagram. We are going to mark. Free body diagram. Free body diagram. I'm expecting you to draw 2 free body diagrams for me. Yeah. I'm expecting you to first draw what we see, then you resolve. Free body diagram. Give me a thumbs up once you're done. Just look at the diagram. It's very straightforward. We are pushing, so there's applied. If we are going up the plane, friction must be acting where? Down the plane. And then you have what? Your normal force. And this is it's a lovely example. Okay, people are done. So what will my first diagram look like? Don't forget where your surface is, right? So what would that be? Normal. What is this? Gravity. What is this? And what is this? Please, the friction must be parallel to the surface. I see some learners draw friction like this. No, it must be parallel. Hence I give you that note, parallel to the surface. Come, let's label what we have. Friction, what do we have? Gravity, what do we have? Normal, and what do we have? Applied force. Everybody okay? You okay? Now let's draw the resolved one. What do? I start by my normal. Once I draw my normal, I complete that straight line. Make sense? Then what do I have? Force applied. FG parallel will be this way. Remember, this is now your working diagram. You can draw anything you want. Where's the surface? This way to guide your FG parallel. And then what do I have? Frictional force, right? Lovely. You can draw it over each other. It doesn't matter. So what is this? Friction. What is this? FG parallel. What is that? Normal. What is this? F. And what is this? FG. Please let me know if everyone is okay with my forces. We okay? Once you are okay here, you are done. I promise you. What is the formula for FG parallel? mg sine alpha. Remember, this is not my working diagram, right? What is this? mg cos. What is the angle of friction, the theta? Friction is always 180. So the angle here, theta here is what? 180. What is the theta here? 0. Guys, you are now fully done. it means you've understood work. We have 6 minutes and we are going to answer now. Did they ask us to do this? No. Will this facilitate your work? Yes. Let's go and answer the first question. Calculate the work done by the cyclist. That is what? Applied force. What is your formula for work? Number 1, work is equal to what? F delta X. Alright, this is general, but they are specific. They said work done by applied. So I'll come here and relabel my W to say W by what? Force applied. This force becomes what? Applied. Does that make sense? Make sense? Hello? Talk to me quickly. You've got 30 seconds to talk to me. Yes? Are you fine? Or you are just saying you're good? Okay, what is my force applied? Do we have it? 20 newtons. Beautiful. So what do I have? 20. What is my displacement? Go back. 32 meters. Aha! See, I've already answered my force. What's the angle? Can you see my free body diagram? Cos of what? 0. 640 joules. 1, 2, 3. Straight to UJ. You are done. Straight to UJ. You are moving. Or vert, whichever one you want. Just get there so you can do W equals to F delta X. They open the gate. No MBT, nothing. Just go in. Quickly. But that makes sense? Good. Use the, look at, work, energy, theorem to calculate the what? Magnitude of the velocity of the bicycle at 32 meters. What are we looking for? Final what? Velocity. I'm going to do this now in 3 ways. I may still 5 minutes. Usual, ne? It's normal. Okay. What are we looking for? Final what? Velocity. We are told to use the work energy what? Theorem. Can we now? This one there are so many options with physics. That's why I don't like marking this topic. Yes, but if we go to the memo, you'll find about 6 options. But I'll do 3. Option 1. W net is equal to what? Change in kinetic what? Energy. That is my work energy what? Theorem. What does W net mean?
The sum of the...
Okay. Sum of all the work. Sum of work done by other forces. Look at your system. Which forces are working here? Work done by force applied, because it's there, right? Work done by frictional force, that's there. And work done by what? FG parallel. Does that make sense? Why am I not putting my normal and FG perpendicular? 0 work. Why? Cos 90 is what? 0, and they are perpendicular. Are we good? What is my change in kinetic energy? Half m Vf squared minus Vi squared. Guys, is it making sense? Once you do your substitution well, boom, you're good. Can I continue? It's just a matter of substitution now. Wait, do I have the first one?
Yes.
Okay. 640 plus, I don't have work done by friction, right? So I'll come here and say, what's the formula? Friction delta X cos theta. Make sense? Plus, this is just the thing that makes it boring. It's long. What about FG parallel? Okay, we can use that quickly, right? mg sine alpha. Wait, I don't want people to get confused. I want to do something. This is long. Can I copy this on the next page? It's long, so I don't want to. I'm removing that. I'm removing this. And I'm putting this right here. Come, quickly, quickly. Running out of time. But I hope the lesson made sense to you. No, I want to expand first. so that we see what to substitute. Yes, talk to me.
So, maybe please repeat number 2.
Okay, we are only substituting now, Ratile. Work energy theorem. What does work net mean? Net means total. There are 3 forces acting. Applied, friction, and gravity. Right? And I said, look, all your forces are here. They're actually 5. 1, 2, 3, 4, 5. But these 2 are not doing any work because they are perpendicular to the displacement. Are we okay, Oratile?
Yes, sir.
And we have 1, 2, and 3. We're good? 1, 2. Once you highlight that, you just substitute now. Work done by friction, delta x cos theta. What about work done by FG parallel? Okay, I want us to quickly do this so that I want to carry everybody along before we start doing shortcuts. Okay, half m vf squared minus what? Vi squared. Okay, can I bring this one down? What is the frictional force? 11. Guys, please don't come here and say negative 11. If it was Newton's laws, I would say negative what? 11. Work is a scalar quantity. I don't have plus or minus here. Do you know where that minus would go? Cos 180. Because cos 180 is negative 1. That's what takes care of that negative. So please, on this one, don't tell me it's acting the opposite direction. No, it's scalar. So what do we say? 11 multiplied by what? 32. Friction is always what? 180. Can you see my negative 11? That's where it comes in now. All right. Plus, what is this one? mg sine alpha delta x cos theta. Okay. This is the only calculation in this question. This is the long way, but I wanted to see it. Okay. Because there are sometimes you have to use this one. 11 times 32 will be what? 352. And it's going to be a negative. 352. Yeah. Cos 180 is what? Minus 1. So put that in your calculator, you get that. What is the mass? They give us mass.
Yeah, 1.6.
Yeah, I think it's either 6.1 or 1.6. I also don't remember. 6.1. I don't know why they would just say 6, man. I don't understand. I must put 0.1 there. 6.1. What is G? 9,8. Sine what? 10. Do you remember that angle is 10? So do you see my difference between alpha and my theta now? What is my angle there? What is my delta x? 32. Cos what? Wait. FG parallel. Where is it? And my theta is what? 1/8. I don't know if what I'm doing here makes sense to you. Half 6,1 vf squared minus 5 squared. Let me know if we are okay with the substitution. I don't want to come back to this. Guys, the rest is just maths now. Physics is done. Yeah, this is where you bring your calculator, right? You will have skipped all of this. Okay, since we don't have white calculators like these people that are bamboozling us, can you give me this, please? Give me that. Very fast, guys, very fast. 640 minus 352 would give... Just this one?
Yeah.
You sure?
100%.
Okay, now add this to it. Minus 352
Let me just check it.
plus 640. Just give me the whole left side. Please let's all confirm, because I'm going to use another method and we must get the same. Guys, the rest is just substitution. Once we break down the formula. Come on, Shamil. You're not confirming, you're waiting. Huh? Shamil, I don't like what you're doing. Negative 44, 182. You're not working, you're waiting for others to do the work. No, that's not right. Half times 6,1.
3,05.
Lovely. 3,05 VF squared minus what? 25. What do? We can divide both sides by what? 3,05. Please give me an answer there.
14,49.
Negative 14,49.
Oh, you want it, so it's 4,859.
Okay, we don't let us round off yet. 4,859 equals to what? VF squared minus 25. Can I move the 25 over? 10,
51409.
okay, 51409. Therefore, what's my VF square root?
3,24.
Meters per. All right, guys. The rest is just maths now, please. You have all science learners. You should be able to. Once we do that, the rest is maths. Are you with me? I'm going to run to the second one quickly because we are out of time. Second option. This option, what am I using? Workmate. Is that the same answer you got?
My calculator is still thinking.
All right, guys, are you okay? Once you get the substitution, the formulas right. We okay? I hope I didn't lose anyone. Quickly, option 2. You can redo this, you know. Option 2. Look at work done by non-conservative is what? Change in kinetic plus change in what? Potential. What is my non-conservative? FA. Wow. Fat. Friction. Do we have friction here?
Yes.
Do we have applied here?
Yes.
Do we have tension? No. So I don't need to include it. So what would I say? Work done by what? Friction plus work done by what? Applied, right? Equals to what? Half m VF squared minus what? VI squared plus mg H final minus H initial. Does that make sense? Because it's mg H final minus mg initial. Does that make sense to you? Now, what is my frictional force? Fk delta x cos theta plus force applied delta x cos what? Theta. I'm rewriting this formula. Half that. Here now, do you notice I am not using anything called sine what not? What is my frictional force? 11. 32. Friction is always what? 180 plus, I think we have this already. 640 equals to what? 1 over 2, 6,1 VF squared minus 25 squared plus 6,1, 9,8. Aha, my good learner, I don't have a final height. I'm going to take you back to the diagram quickly. The object was starting from the ground, right? So my initial height is what? I want to see where that sign disappeared to. Go back.
Oh, you're going to use 3 sides.
That is it. That is where my sign disappeared to. Because what is sine? Sine 10 is what? That is that sign that is now disappearing. Trig ratio. So what is H? 32 sine 10. Can I show you that 32 sine 10?
Because of 90 is what? Because of 90 plus 0.
Wait, can I show you that 32 sine 10? Wait, let me write this first. I won't even calculate this. 32 sine 10 minus 0. My good learners, please, I'm not going to calculate this. We have this plus 640, right? Watch this. 1132 cos 180 plus 640. 1132 cos 180 plus 640. Okay. What do we have here? Half 6,1. Do you see this? Okay, let's go back. It's on the right hand side. Now watch this. What do you see here? 6,1, 9,8, 32 sine 10. Because 32 sine 10 minus 0. Are you with me?
Yeah.
I want to show you where this is. Do you notice it's on the right hand side here? Come here to this equation. Check. 32 sine 10. And what? What do we have again?
0.8.
Let's see. Do we have, okay. 6, 1, 9, 8, 32 sine 10. Look at it. 6, 1, 9, 8, 32 sine 10. Cos 180 is what? If I move it over to that side, it becomes what? Can you see that it's the same thing?
So,
Yep.
5f squared. So it's supposed to be minus 5 squared or 25 squared?
Oh, minus 5 squared. Once you do this, you are going to get the same answer. But I have moved away from what? mg. That mg is FG parallel. Because I'm using work done by non-conservative force. I think we can shut it down here.
If I use the mechanical energy,
Formula.
yes. So the mechanical energy before is equal to, at the bottom is equal to mechanical energy at the top.
It's not equal, it's not the same. It's not isolated system. If I want to use that, I'll have to say plus the work done by friction, that fat guy.
So I can do that.
Yeah.
Can I just add the friction?
But you have to add friction to it because the system is no longer isolated. There's a fat guy that you gave 5 rand to. You have to take care of that 5 rand. But guys, for me, I love this formula. I don't have to worry about so many things. So they even give you the height in some cases. Here they didn't give us the height. That's why we had to use 32 sine what? 10. But sometimes we are given the height. Is it compulsory to include weight parallel? No, it's not. That's why I did this formula. I didn't include any weight parallel here. Musa? Do you want to help me? Let's just get this answer. 532. 532 plus that will give us what? Oh yeah, negative 532.
Plus this one is 5, 3, 2.
Give me a calculator quickly. Just help me solve this. Huh?
1,
My head is tired.
or something.
No, don't lie to me.
Yeah.
1?
So
Huh?
you want to calculate.
Just press it. 640 minus 532. 1?
108.
What's that?
108.
What's that? You mean 108?
Yeah.
Not 10. Okay. What is this? 3,05 df squared minus what? 25. What would this give me? Quickly. 6,1 times 9,8 times 32 sine 10. Chapter. If it works up now, you are done. You have finished typing a whole passage.
$332.18.
332, comma what?
18.
Can I take that 332, comma 18 over? What will it be? We take that over, it becomes a negative.
Minus 224.18.
224.
0.18.
Are you guys sure? These answers, these answers are looking very different from what we got. Divide both sides by 305. These answers are looking very different. I can feel.
Negative 73.5.
Our answers are not correct. We've done something wrong somewhere. People, please. It's either this one is wrong or that one is wrong. Can we please fix it? Please, before we go. We're not going anywhere. Can we do this correctly? Please, let's so that we go and correct that one. Yes?
So on the left-hand side, it was supposed to be 288.
288. Jesus, guys. Okay, 1 second. I don't understand what these people here are giving me. 640 minus that.
288.
Uh-huh.
The mistake is there. Instead of 108, it's supposed to be 288.
288. Now that 288 minus 332, comma 18.
Negative 44.18.
Uh-huh. Negative 44,18. Thank you, Ratile.
0.05.
Good.
Negative 14.49.
If you divide 44,18 divided by what? 3,05. We get what?
Negative 14.49.
Okay, let's not round up. Plus the 25 equals to what?
10.51.
Good. And then we have our VF.
3.24.
3 comma?
24.
Meters per second. Guys, all right, guys. You see, the choice is yours. Both formulas are correct, and you just need to know. Explain why frictional forces are regarded as what? They're asking you to define. Because the work done depends on the path what? Taken. Good night, everybody. And that's it. I hope it makes sense. What we are left to just talk about is work, is power.
So it's just path done.
Musa, once I say W net, then I must include all the forces. So work with the formula you are using. Once I say W net, I must include that. But if I'm using work done by non-conservative, gravity is not a non-conservative force, so it's not there. So don't cram it. Once I say non-conservative, it is friction, applied, and tension. Do you notice I am not talking about gravity? Just follow the principle and you're good. Musa, is that fine? Non-conservative is friction, applied, and tension. Just use that and you're good. Okay, awesome. So just work with the definitions, work with the formulas. Don't say you have not put gravity. It has already been taken care of in it. Okay. All right, guys, have a beautiful evening and keep well. Goodbye. Awesome.